Functional grouping and criticality assessment in plants. Introduction. The criticality of an instrumented function in a process plant is a measure of its importance to the plant's smooth operation. Any disturbance to a critical function impacts production and may cause the process to become unstable, unsafe, or result in a plant shutdown. Functional grouping determines the instrumentation related to a specific control or trip function or a group of closely interrelated and interacting control trip functions. Functional grouping. Functional grouping segregates the plant into various systems and subsystems. A system includes the minimum grouping of plant control functions and associated interdependent equipment with a common purpose. Failure of any part of a functional group affects the whole group. Subsystems can be identified within each functional group. Safety instrumented system functional groups. An IPF loop consists of initiators, the IPS, and final elements. The group is defined by a common output logic function. Cutover may require temporary parallel operation if inputs are part of another function. Control system functional groups. These relate to process unit control, such as a vessel or reactor, where parameters like pressure, level, temperature, and flow are interrelated. A block diagram illustrates the segregation of systems' subsystems. Functional grouping report. Based on system-subsystem segregation and analysis, reports are prepared for IPS and control system cutovers. The format is provided in Attachment 4. Criticality assessment. Applicable codes and standards. DP 32.8.10.10-Gen. Classification and implementation of instrumented protective functions. ISTR 91.02.2003. Criticality Classification Guideline for Instrumentation. AG 181 Rev 2, Field Bus Foundation System Engineering Guidelines. HCF Lit 34, Heart Communication Foundation Field Communications Protocol Application Guide. Criticality Classification General Principles. Evaluate systems, subsystems, and equipment in terms of life safety, environmental hazard, plant safety, and potential production loss. Systems with significant failure consequences must be further analyzed. SIL 1, SIL 3 Instrumented Protective Functions, IPFs. IPFs are generally ESD, fire and gas, HIP systems, or machinery protection systems. Criticality is related to the SIL rating. Failures of safety systems lessen the chance of dealing with hazards, but do not create hazards. Class C2, Safety Critical Control Systems. These systems keep process parameters within safe limits. Failure can cause hazardous situations, but does not require detection of specific emergency conditions within the system. Systems must be robust to avoid spurious shutdowns and may be backed up by primary safety devices. Class C1, Critical Control Systems, Non-Safety. These systems control product quality and throughput. Failure does not create hazardous situations, but can cause shutdown or product quality deterioration, impacting revenue. Class 0, Non-Critical Control and Indicating Systems. These systems provide information not directly related to product flow control. Failure causes minor inconvenience. Criticality Rating Procedure. Use of the procedure. Define and list all systems or main equipment items. Analyze subsystem criticality using methodologies like quantitative risk analysis, QRA. Comments and clarifications assist in explaining system nature or function. Hazard identification. Review process documents to identify credible events causing hazards. Determine the sequence of events, causes, consequences, likelihood, and risk associated with hazardous events. Consequence listing. S. Life safety. Risk to personnel from failure. E. Environmental. Risk to the environment from failure. Plant safety. Risk to plant process units or structures from failure. H. Hidden. Failure does not result in immediate consequences, but can lead to significant risks with further failure. R. Revenue. Impact on revenue or investment return from failure. And none. No significant consequences from failure. Risk assessment. Assess potential risks from malfunctioning instrumented systems. Risk evaluation considers worst credible cases during cutover activities. 4 major risk categories: risk of loss of critical control, risks from plant modifications, operation, maintenance during cutover, risks from construction, installation errors, risks from process dynamics and cutover duration. Risk mitigation. Mitigation methods: reduce or eliminate risks for safety, Precautions minimize hazards with additional work methods. Selection criteria for risk control countermeasures: effectiveness, feasibility, cost, risk for facilities during cutover, general power failure, ensure UPS power sufficiency, communication failure, review and publish communication procedures, human error, review staff training and cutover procedures, unintentional operation, review and amend control system procedures, fire gas alarm demand, review and publish emergency procedures, cutover duration, quick output transfer to maintain safe operational conditions, consider process safety time, PST, to ensure safe state during cutover. Cutover classes: hot protective system cutover. Old and new systems operate in parallel. Hot control system cutover. Old and new control systems operate in parallel. Conclusion: review all signals to and from control protection systems and produce cutover work packs. Following mitigation methods and precautions ensures safe cutover activities. Attachments: 1. Overview of functional grouping. 2. Overview of criticality analysis. 3. System-subsystem criticality classification block diagram. 4. Cutover risk assessment and functional grouping report format. 5. Cutover category assignment.